Our new system called SemARFlow injects semantics into unsupervised optical flow estimation for applications to autonomous driving. Optical flow is pixel-level motion. It is defined as the 2D displacement vector pointing from one pixel to its corresponding position in the next frame. We estimate optical flow for every pixel in each frame of autonomous driving videos. Labeling optical flow is difficult, and unsupervised estimation is therefore especially important. Most current unsupervised methods are based on photometric and smoothness constraints. These may fail in the presence of occlusions, motion boundaries, poor texture, and illumination changes. Therefore, our idea is to investigate whether adding additional information, such as semantic domain knowledge, can help better constrain the model. Specifically, we use a separately trained, off-the-shelf semantic model to segment the input images semantically and add those inputs to the network. These new inputs provide prior knowledge about boundaries and motion patterns. We show in our experiments that this knowledge improves the unsupervised flow network significantly. Our network is adapted from SemARFlow. We first add a semantic branch in the encoder to extract and fuse semantic features. We then add an upsampler network in the decoder to learn how to upsample flow based on semantic information. We also turn off the smoothness loss because we find it to conflict with our learned upsampler. To better train our network, we also propose a semantic augmentation module with self-supervision. Specifically, similar to SemARFlow, we first estimate flow and compute photometric loss in the first forward pass of the network. Then, we extract vehicles, street signs, and poles from some other random samples. We copy and paste these objects into the current training sample to generate a new augmented sample as well as its pseudolabel. Finally, we estimate flow for the augmented sample in the second forward pass, which is self-supervised by its pseudolabel. This strategy helps better train flow in occlusion regions and around object boundaries. In terms of results, our final model outperforms all previous state-of-the-art methods by a clear margin on the KITTI benchmark. This suggests that semantic inputs can improve unsupervised optical flow estimation significantly. From our qualitative examples in the last column, we see that our flow outputs are consistent with the semantic segmentation inputs and have much sharper boundaries around objects. To better understand how each semantic class benefits from our method, we compare the flow errors of different semantic classes before and after adding semantic inputs. Most of the improvements are from pixels on the cars, which are exactly the key objects in autonomous driving. We also investigate our model's generalization ability by training on cityscapes and testing on KITTI. The results show that adding semantic inputs also help the model generalize better on new datasets. For more results and details, please refer to our paper and code. Thank you.